Okay, please go ahead and start.
All right. So hello everyone. Welcome to today's good evening. Welcome to today's joint seminar. And today I'm going to present a paper in ICLR 2021. Its title is Free Launch for Few-Shot Learning, the Distribution Calibration. So here it's outlined today. I will first give you the brief introduction of this paper, talking about the background of few-shot learning. And then I will introduce you to the main approach of this paper. Finally, the experiment and their conclusion. So we first talk about the background of the few-shot learning. It is raised by a very simple question from the land Turing. So can the machine think? We can now claim that the machine learning performs pretty well in computer vision and natural language processing. However, the way to do so still relies on the powerful devices, advanced models, and large data set. So one should not be too surprising for the first two because the human brain is actually complicated. But for the large data set, it is the point that people question the most. For the human learner, even the baby can learn from very small amount of data. So even in the one-shot or zero-shot settings, the reason behind is because of the prior knowledge. So to imagine a tiger, we know as human, it is somehow like a bigger cat with a funny figure on his head, looks very familiar, very similar to a Chinese character, but the machine cannot do that. So let's revisit the few-shot data set and what they're trying to do. So for the training, there exists a base data set, and it contains a number of base classes, and the data samples for the base classes are sufficient. And on the other hand, the support data set contains several novel classes, but they only have very limited data samples in novel classes. Such settings that several classes do not have enough data samples is actually very natural. Because some classes cannot easily sampled, it is because it is rare in nature, so we cannot easily sample them. The number of the base classes is denoted as CB, and the novel classes we denoted as CN. The terms of NVK shot is to describe the size of the support set. So if you look at this figure, this figure, the 4 ways means they have 4 novel classes, and the 2 shot here means for each classes they only have 2 data samples. And at last, the query data set means there are test data samples, which is never seen in the training. So the notation is shown in here in the blue box, where the support data set we put an S to show the support data set, and for the query data set we name it as the set Q. So what this essentially makes the few-shot learning very difficult. Maybe you can refer to this figure. We can somehow know the reason. For the left figure, when we have sufficient data, the big H here is actually the hypothesis space that we want to search for an optimal solution. With some initialization, we start at this triangle, and the oracle solution is here. We name it as H hat, where it can possibly outside our scope. So what's actually we can attain is the H star. The overall ultimate goal is to learn from the start to the H star here. But because we are estimate this H star, we use lots of data samples to generate an empirical loss. By solving this empirical loss iteratively, actually we end up with HI here. So the gap between HI and H star is the estimation error, and the H star to the H hat is the approximation error. So if we have large data, the error can be small and the accuracy of the classification can be good. But when we only have small data samples, for example, in the few-shot learning, we have large estimation errors. So we end up in the HI here, which is far away from the H star and H hat. So it is actually not desired. So it somehow explains the overfitting, actually. So to solve this problem, the few-shot solutions will adopt some prior knowledge in three aspects. The first, they can use particular models to narrow down the searching spaces, such as some pre-training, fine-tuning process, or lots of works on the parameter sharing or parameter tying, something like that. Another way is to update the parameter using some prior knowledge. So it may need less data samples to get to the acceptable H hat. And the last way is to actually augment the data samples for good generalization. This paper falls in this category. They augmented the data or augmented the features, in fact, for good generalization. So talking about this paper, there are two nonsense here. The first one is the model trained with a wide coverage of data. They can generalize well, but for the few training data, it can overfit, so the result cannot be accepted. What they are trying to do is showing in this plot. We know that it is a feature before the classifier is to be classified, and but in the few-shot settings, we only have one data samples for each label, so it can definitely cannot represent the ground truth distribution showing in the colored shadow here. So as a result, the classification boundary is incorrect, and the classifier will be poorly performed. We can see the black lines are the learned class boundary, so it's only overfit to these three data samples. What this paper trying to do is showing in this subfigure. They want to generate extra features to represent the true distribution. So if it works in this way, we can have corrected learned class boundaries, and the classification accuracy can improve accordingly. The first questions to answer is why they want to generate features instead of data. So the reasons behind are twofold. The first one is they also claim that comparing to the raw data, the feature may have much smaller dimensions, so it can be easier to calibrate a feature distribution, and it can be more effective in the classification. And the second reason is from the previous work, they know that the deep features follows somehow in the Gaussian distribution. So one only need to estimate the distribution by estimating the mean and variance. So the parameter should be less to generate. And the other fundamental problem is how to generate augmented features. They made an observation on this right-hand side table. So suppose we have an unseen or a novel class called Arctic fox. So as human, we know that the Arctic fox should be white, and it can look very similar to the white wolf. So keep this in mind. The author compared the deep features of the Arctic fox with some alike and some alike objects like white wolf, and some disalike classes like jellyfish and orange. So we can show the result of the similarity measurement. We can see the main and variance of the alike data set and alike class in the base classes. The distribution can be very similar to this novel class. So it is, as a result, they want to borrow the alike classes to help calibrate the distribution of a novel class. And they use these calibrated distributions to generate some virtual features and to augment the classification. So these remaining works can be straightforward. First, they estimate the distribution of a novel class, and they use this distribution to generate the virtual features. And at last, they perform a supervised learning to retrain a classifier for the task-specific classification. So here is the overall what they're trying to do in their paper. So let's move to the main approach and the algorithm of the distribution calibration. So here is the main algorithm. As you can see, it's quite simple and there's no very complicated math and model design. So the algorithm is trying to learn from the both support data set and the base data set. So they're using some backbone feature extractor. They extract the features from the support data set. And they also do extract the features from each data samples in the base class data set. And they calculate the mean and variance for each base classes. In this step one, in order to make this, this is for the base classes in the base data set. So because their some data samples are sufficient, it is directly resulting in Gaussian distribution. But for the NVK short support set, because their data is insufficient, they want to perform 2 key ladders of power transform to make their few data samples more Gaussian-like. And the next step is for each novel class in the support set, they use the base set statistics in the step 2 to calibrate the Gaussian distribution for the novel class. And they use this calibrated distribution to generate new features and train a new classifier. So I want to point out that this classifier is actually a task-specific one. So they only want to solve the classification problem that they want to label all the data in the query data set to the classes in the support data set. So that is the main algorithm of this paper. To be more specific, they calculate the base class statistics simply by calculating the mean and variance from each data, each base class, the mean and variance in each base class with massive data samples. And for they only perform the 2 key ladders of power transforms in the support data set. So it is showing in this equation is the power of the original feature vectors if the lambda doesn't equals to 0. And if it equals to 0, it takes the logarithm. So generally speaking, the lambda here is a hyperparameter. So to be generally speaking, tuning this lambda here is to adjust the distribution, a Gaussian-like distribution from positive skewed or the negative skewed to the centered one. So this is actually a dataset. It is actually a dataset dependent parameter, and also will show that in the evaluation. So this is just a hyperparameter. And with this, with this calibrated statistics, and the transformed support data, the next step is to choose some similar classes from the base class to evolve in the calibration. So the similarity metric is actually an L2 distance. They select the top K closest base classes, and for each novel class, and they name this set called SN. And subsequently, they're using both the selected SN and the transform data X tilde. They are calculating the calibrated mean and mu and the covariance sigma. We can see the calibrated mean is generated from the selected top K similar base data set and the data from the supported set its own. But for the covariance, because we only have few data sets in the support set, it is estimated from wholly from the base data set. And there exists another hyperparameter called alpha. It is to indicate the dispersion. So in the end of this algorithm, one should leverage this calibrated distribution to generate the virtual feature samples. And they have this augmented feature set dy following the calibrated Gaussian distribution. And at last, the task-specific classifier is trained with the supervision of the cross-entropy loss. So let's move to the experiment. To show their effectiveness, the distribution calibration. Okay. What happened? Sorry. There is here. Please wait a second. My computer shut down. All right. Sorry, let me boot a little bit.
So Chenpei, when you restart the computer, I want to ask a quick question. So
All right.
it seems they only do something like the data augmentation, right?
Yes, it's true.
And they try to generate some Gaussian distribution and select the top K.
Similar classes in the base data set.
So, Chenpei, so oh, Dr. Pan, you can go ahead.
No, Dr. Ray, go ahead. I'm thinking about my question. I'm thinking it's kind of simple, yeah.
Yeah, I'm also trying to figure out how it works. So it's like this, like you have base class, and you have also have this support set. For the support set, like you want to like find some similar one, and because this supported set you have the label, so you just rely on this supported set, like to do the data augmentation. But you can guarantee that the variance and mean so will be very close to the base class. Is it like this?
Yes, I think it's just you have the support set, and for each novel class, you choose the very similar classes from the base set. Yeah, and they use the base set statistics to generate the distribution, and they use this distribution for a classifier training. Yeah, it's look like this.
Okay, I see. I think so. Why don't use this novel like the novel class supported set like to do the data augmentation? Why it need to? Let me see.
Because the novel set doesn't have the enough data samples.
Okay, I see. So he want to generate like the diverse data for the base set, the base class. So that's for the base class, it will have the enrich the feature, right?
Yes, something like that. Yeah.
Okay. I think probably I'm not sure. Probably get to the point. Okay, thank you.
So the base set, if we do the classification on the base set, they're going to have some, I don't know, ground truth classification. The base set is always correct, something like that.
No, for the future learning settings, they can do anything on the base data set because the classification is task specific. They only want to label the unseen data that is from the novel data set. So for the big big data set like base sets with massive data samples, they're trying to use the statistics so they can transfer something from the large base set to the insufficient support set. So that's they're trying to do.
Okay.
Sorry, Dr. Pan, what's your
I'm thinking about the example you gave. For example, there's a new label, right? So we can classify that one to Arctic fox, right? So
right.
If in your base set you don't have this label, the normal label, so are you going to generate according to the white wolf? So the finally is going to be classified as white wolf, or?
No, it's find the most classic. For example, they find the white wolf is the most closest one.
Yeah, and they're going to use the white wolf's data distribution to augmented Arctic fox data distribution.
Yeah, that's they're trying to do. But the Arctic fox, they only have very limited data samples, but they do have data samples. So they are trying to, it is called calibrate. So they use this this distribution to calibrate this distribution.
To calibrate.
But they do not reuse them or totally use white wolf for label them as Arctic fox.
They try to choose the top K closest to Arctic fox, this kind of data set.
And they somehow fuse them together.
Fuse them together to build up, the kind of data distribution for the Arctic fox, right? Something like that.
Yeah, it's true.
And based on the augment data set, they do the classification.
Yes.
Okay.
Yeah, but they're not using the the raw data, they're using the deep features. So they may have these two properties because the features has lower dimension and they are told it's Gaussian distribution. So it's more reasonable to use Gaussian, such a simple distribution.
I saw several papers that talk about, the features that follow the Gaussian distribution. So now that is, that one is kind of proved, or that is, empirically summarized by different papers?
We have some original data showing that the features can be Gaussian distributed, but yeah, actually I choose this paper because Dian in last week they present a very similar paper. They are seeing this.
In Dan's presentation, he always that paper also mentioned, all the features follow the Gaussian distribution, but I think their claim are not that strong. They just say the most of features follow Gaussian distribution. So that's the reason why I want to know is it proved fact, or is just people empirically summarized? Okay, say most of the features follow this Gaussian distribution.
Actually, they list several references, but in their paper, they do use they calculate the maximum likelihood estimation instead of in their evaluation. If the Gaussian distribution assumption is true, the MLE estimator will give consider a comparable result as a modern classifier, and it does. So maybe this assumption is true in some semantic context, like the computer vision or something like that. Yeah, I saw their evaluation, and I believe for this task, the Gaussian distribution is true. And even it's not actually perfectly Gaussian, they use this power transform things to make them more Gaussian-like. So they have some plan B here. Oh,
okay.
So here, okay, let's move on. Sorry for the computer stuff. And here is the experiment setup. They're using these 3 different data sets. The first 2 are actually sampled from a larger data set, and CUB is a fine-grained data set for some birds. And the feature extractor, because if you remember, they are calibrating and generate features. So they definitely don't want the feature extractor to be updated, making the feature distribution drift. So they are using some fixed feature extractor. You use the wide ResNet in the rest of this paper. And for the classifier they're using, the author claims that even a very simple logistic regression and SVM classifier can beat the state of the art. So they're using this two simple classifier for evaluation. And here are all hyperparameters they're using. For the performance metric, they're use the top line accuracy on both 5-way one-shot setting and the 5-way 5-shot setting. So here is performance comparison to the state of the art. And I believe it is their remarkable performance improvements make this paper get accepted. The evaluation is made on 5-way one-shot, 5-way 5-shot settings on both mini ImageNet and CUB dataset. It actually made on the other, because the third dataset, but I did not list them there. They compared their DC algorithm with some less related optimization-based methods and metric-based method. And they also compare it with some more related generation-based method. And you can see we can have 3 conclusions here. First is for the simple linear regression and SVM classifier, aided by the DC algorithm, they outperform all the state-of-the-art methods. And even for the maximum likelihood, it actually is not training. It's just to use the generated feature distribution. They actually outperform the others as well. So the DC algorithm is effective in comparing these results. And we can also find nearly 10% margin for the DC algorithm. It beyond this generation-based method. And this method, for the generation-based method, because, for example, they're using GAN, they need to have massive learnable parameters in the training to generate, they need to train the generator for the data augmentation. But as you can see in this algorithm using the the distribution calibration, there is actually no training for the generator. So you can save you can save significant training time and computation resources. So that is performance comparison. And they also did the visualization of the generated samples. For the first subfigure, it is a five-way one-shot. It is the five-way one-shot support data set. So all we have is this 5 novel classes, and each class has only 1 data samples. So imagine we are doing classification based on these 5 points. It can very easily goes to the overfitting. And the subfigure B and subfigure C is the process of generating the virtual features. So we can it can somehow reflect the distribution of the novel classes, and comparing to the subfigure D, that is the ground truth data distribution in the query data set. You can see this calibrated distribution can correctly reflect the ground truth distribution. So that is the reason why the distribution calibration can effectively train a few-shot classifier. So that is their visualization result. And the author also mentioned their DC algorithm is an add-on algorithm and can be applied to different backbones, feature extractors, and baselines. So they add their DC algorithm to several backbone feature extractors with and comparing them to the one without the DC process. So we can see about 10% margin of this DC algorithm applied to almost every backbones mentioned in this paper. And for the baselines, for the other baseline method, for example, the baseline and baseline plus is actually a matrix-based few-shot learning method. They apply the DC to this existing method, and you can still have a 12.51% improvement comparing to the no DC ones. And here is the role of the Tukey's power transformation and feature generation. So we know that we have more generated features or data samples, it can boost the classifier training. But what is the role for the power transformation? So on the left-hand side figure, we can see the lambda here is a hyperparameter in the Tukey transformation. And you can see the optimal point is around 0.5. Remember that this transformation is to make a distribution more Gaussian-like. So for each data set, for example, in the mini image net, you apply a 0.5 lambda to the data set. is actually a square root of the feature vectors. It can significantly improve the test accuracy. And at the neighbor of the 0.5, we can see the red line representing the one with the generated features is outperforming the blue line, that is the one without generated features. So for the 2K power transformation, if you use a reasonable lambda for the specific data set, it can boost the performance. And for the feature generation, if you choose one reasonable lambda, there is no doubt that if you increase the generated features, the five-way one-shot accuracy can correspondingly increase. So here is for even for the one with the transformation and the one without the transformation. And at last, we also concern about the other hyperparameters. So the first one is the K. We choose top K similar classes from the base data set. So we know that if we choose a smaller K, it may not perfectly reflect the ground truth distribution, but if we have a much bigger K, or we say the K is too big, it may involve several irrelevant or not the classes that is not that similar. So it can hurt the accuracy. So in this paper, in the mini image dataset, ImageNet dataset, they also find that when K equals to 2, it will give us the best result. And for the other hyperparameter is the dispersion of covariance matrix alpha. And in this subfigure, we can see for both testing data set and validation data set of all these three mini ImageNet, CUB, and tiny ImageNet, they all have the same tendencies. So they conclude the hyperparameter alpha is a dataset dependent hyperparameter rather than some data overfitting to some data samples in the query data set. So if you are using them on one data set, you can use the you can use the one hyperparameter. If you are adopting another data set, you are using another alpha for the hyperparameter tuning. So that's the concerns on the hyperparameters. So at last, let's draw the conclusion. At first, they propose a relatively simple but effective distribution calibration strategy for the few-shot classification. And without much parameters to learn, the simple logistic regression trained with generated features will outperform the current state-of-the-art method. And in the end, the calibrated distribution is visualized and demonstrates an accurate estimation of the feature distribution. So that is all for today. And any questions?